Hi there, I want to do a quick walkthrough with you for the midterm 2 exam. So let's get started. We start from multiple choices. So the idea here is once you're familiar with the concept, it shouldn't take you more than 30 seconds to finish every question. So let's read it together. First question, delta S must be positive in which of the following processes? So when we say positive, we're talking about irreversible processes. And we didn't specify any specific things, right? So when we're saying positive, we're talking about an irreversible process, and it must be in an isolated system. So we do not have exchange to the surroundings. Now, next up, which of these cyclic integral will vanish for a closed system with PV work only? So this actually asks you, when we say a cyclic integral vanish, it's asking you to use your thermodynamic knowledge to identify a state function among the following options. Now for the cyclic integral of PdV, so this one is negative work reversible. This one is work reversible. And this one is Q reversible. So all three of them here are line integrals. So the only answer must be D. Next up, which of the following quantity have the same dimension as entropy? Now this one is pretty straightforward. One of the definition of entropy is the Boltzmann constant times logarithm of probability plus a constant C. So your entropy must have the same unit as your Boltzmann constant. The longer way is to write out the actual unit for entropy and for each of the term here. But this one is faster. 1.4. Which of the following quantities does not have the same dimension as VDP? So we see VDP in our Gibbs relations. Now in here, you have G, H, and A. These are all have the same dimension as your VDP, but your entropy is not, right? So your SDT will have the same unit as VDP. Next up, which state function is being described using the following statement? It is maximized when an isolated system reaches equilibrium. So this one is quite straightforward. We have, remember our curve here, right? You have time, you have entropy, and we reach to a point. Right? At the equilibrium, your change of entropy equals to 0. And before equilibrium, your ds is larger than 0. So we're looking at C. Next up, combustion of C8H10N4O2 in oxygen forms CO2, H2O, and NO2. So write a balanced chemical equation, and we know the coefficient in front of CO2 is 16. So C8H10N4O2 plus oxygen gives you 16 CO2 plus H2O plus NO2. So in here, on the right-hand side, you have 16 carbons. We must have a 2 in front of your molecule, C8H10N4O2, and you count. Now, all the hydrogens are in water, so here we have 20. It must be a 10 in front of your water. We have 8 nitrogen atoms, so on the right, this must be 8. Now we count the oxygen. On the left, we have 4. On the right, you have 32 plus 10 plus 16. So that's your, has to be 58 minus 4. So we're looking to have 54 oxygen atoms. So that's a 27 in front of it. And now your oxygen is your reactant. So we're looking at C. Now for this question, some people answer D, and I also give you credit because you at least identify that for oxygen, it must be a negative number in front of that stoichiometric coefficient, but the actual result should be C. All right, next up, we're seeing the 0.8 mole of your CH10 and 4O2 reacts. Find the extent of reaction. So if you remember your extent of reaction times the stoichiometric coefficient, well, gives you the delta N of that specific species. So in this case, we're looking at C. Your stoichiometric coefficient is unitless, so your extent of reaction will have the same unit as your number of mole. All right. And in this question, if you answer A, I also give you credit because I assume you write down this balance equation differently with a 1 here and a 8 here. But given whatever we provided, it should be C. But yeah, if you say A, at least you recognize the number of mole as a dimension of your reaction extent C. All right, next up, what is the unit of your chemical potential term? So this one is just it's the same unit as your Gibbs free energy. Okay, which of the following expression equal to the partial derivative of G over T at constant P? So this question actually has two answers that are equally valid. So using the Maxwell relations, we have the partial derivative of G over T at constant P equals to negative S, which also equals to the partial derivative of A over T at constant V. So B is correct. Now D is also correct. So this comes from that rule where you write the partial derivatives together. Their product ends up to be negative 1. So D is also correct. All right, this last question, which of the following expression is equal to partial derivative of G over T at constant P? So we already used it here. So that's D. All right, so that's our multiple choices. Next up, true and false. So this reaction here, we derived it in class together, and this one is actually just generally true. We didn't make any assumption during the derivative process. So when we say this one is only true for ideal gases, the answer is no. Next up, the G surrounding plus G system. So the addition of this term gives you G universe. Now, if we consider all reversible processes, the delta G of the universe equals to 0 because it's all reversible. So when your delta G is equals to 0, that tells you there's no change in your total Gibbs free energy of the universe. So this is true. Next up, entropy S of any system maximized at equilibrium. So this one you just have to double think whenever you see a statement saying like any. For example, if you go back to some of the questions here, like this one, you actually have the answer right here, right? It is maximized when an isolated system reaches equilibrium. So we're talking about isolated system. Next up, if phase alpha and beta of I are in equilibrium with each other, then their chemical potential are equal. So this is false because we're missing one criteria. This must be a closed system. Means you can't have material exchange with the surrounding. Now 2-5 and 2-6 are connected to each other. So I'll start from 2-6. So this one is just writing the derivatives out or writing the differential out. There's nothing wrong with it. But when we're looking at the relationship here, what we're doing is taking the integral of your TdS and SdT. Now this term here, the derivative of du, does equal to delta u. But these two terms, the differential of TdS and the differential of SdT, not necessarily equal to the T delta S or S delta T, because your T and S might be dependent on each other. All right, so this one is false. 2-7. The rate of change of delta H naught with respect to T equals to delta Cp naught. So this question asks you for the temperature dependence of your delta H. So if you're looking in your textbook, you should find the equation. Well, we're talking about the delta H temperature dependence, and that is in 5.5. And we're talking about equation 5.18. And well, in that case, you have delta of delta H naught over dt equals to delta Cp naught. So this one is true. Right, I don't pretend I remember all the equation, but at least I know where to find it. It says the rate of change of delta H naught with respect to temperature. So we're looking at delta H naught, which is the standard enthalpy of a reaction, and the temperature dependence of that reaction heat. You can find your information in the textbook according, or lecture note accordingly. 2-8. The standard state of a pure gas is a pure gas at pressure at 1 bar pressure. So this one is wrong because the standard state of your gas should be ideal gas. All right. Then chemical potential of a pure ideal gas goes to infinity as pressure goes to infinity. So this one is true. This one is one of the figure we've seen together in class, where you have the chemical potential goes with pressure, and it sort of like go like this, just go to infinity. All right, next up. For any isothermal processes that involves only substances in internal equilibrium, the entropy change goes to zero as temperature goes to zero. So this is the exact same wording for your third law of thermodynamics. And that is true. So for true and false problems, the idea here is they should be really straightforward. I mean, even if you don't remember the exact equation, you should be able to quickly find out that information in your textbook. All right, let's move on to short answer problems. Now, for a set of quantities, u, v, delta H, mu, s, all quantities except one have something in common. So I see two different kind of answer here. Both of them are correct. One is we identify the chemical potential mu to be different because all other functions are extensive. Or I also have students say v, saying like all other functionals have some form of energy. Both of them are correct. Next up, derivation problem. Verify that this partial derivative equals to Cp minus Pv alpha. So in order to do that, let's just write out the definition of these terms. So Cp equals to partial derivative of H over T at constant P. Alpha equals to 1 over V partial derivative of V over T at constant P. Now we have enthalpy here, and we have internal energy in the question. We also need the definition. So U equals to H minus PV, or H equals to U plus PV. It's the same idea. And now let's write out this differential. So the partial differential of U over T at constant P would equal to partial differential of h over t, constant p. Well, p is constant, so we can take it out. That's partial derivative of v over t at constant p. Now this term here, that's just a definition of your CP. And this term here equals to alpha times b. So this whole thing equals to CP minus PV alpha. All right, so the way to approach this question is to start by writing out the definition of all the things you see relevant in here. Next up, now considering mixing of inert perfect gases at constant P and T before the mixing, we have on the left-hand side Na equals to 3.0 mole, on the right-hand side Nb equals to 1.0 mole. Now calculate your delta S mix using the second law of thermodynamics. So the equation we're using is delta S equals to negative NaR ln chi A minus NbR ln chi B. All right, so that's your that's the beginning of the coverage of this lecture, or the end of chapter 3 when we talk about mixing of inert perfect gases. You can also use this equation, delta S equals to NaR ln V over Va plus NbR ln V over Vb. Both of them works. But starting from there, let's plug in our numbers. So we have delta S equals to negative 3.0 times 8.314 times ln. So chi A here, that's a mole fraction. That's 3 over 4, right? So the total number of mole is 4. 3 over 4. And this whole thing minus 1 times 8.314 times ln 1 over 4. We plug in the numbers using our calculator. So that equals to negative 3 times 8.314 times ln 3 over 4 minus 1 times 8.314 times ln 1 over 4. And the result gives you 18.71 joule per Kelvin. Right. Next up, using this new definition of entropy to answer the question. Now, in this question, what do we know? We know that delta mix S equals to K ln P plus C. Now, in this case, we're talking about, S equals to K ln P minus C. So delta S equals to K ln P2 over P1. Right, so here your P2 is effectively 1 at equilibrium. And your P1, you have to think about it. So what is the probability of getting the left state? Now your P1 is expressed as 3 over 4 to the power of number of mole of your atom A times 1 over 4 to the number of mole of your atom B. Your number of mole of atom A equals to Na times Avogadro number, and your Nb equals number of mole of B times Avogadro number Na, where Na Avogadro number is equal to 6.022 times 10 to the 23 mole. All right, or you can write this as 3 over 4 to the power of number of mole of Na, 1 over 4 to the number of mole of Nb, and to the power of Na. So P1 is on the bottom here. So our delta S, after plugging the number, equals to negative Boltzmann constant times Avogadro number, ln 3 over 4, negative 3, times 1 over 4, negative 1. Or just effectively equals to negative r times ln, or negative 3 ln 3 over 4 minus 1 times ln 1 over 4. So this expression is the same as you've seen before, so your number will bound to be the same. All right, next up, derive the Gibbs-Holmes equation. This one looks complicated, but it's not as complicated as you might think. So first of all, we have G in my expression. So let's just write out the definition of G equals to H minus Ts. Now in the hint, we say the heat capacities are key properties since blah, 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 blah. So let's write out the definition of heat capacity. Since here we have our enthalpy, it's likely to use the definition of dH over dt constant P. We also have S involved, and this goes to our one further definition or derivation in class, that your heat capacity at constant P, Cp also equals to T times the partial derivative of S over T at constant P. That's all we need. Let's start it by writing out our derivation. So G over T equals to H over T minus S. So the partial derivative of G over T over T at constant P thus equals to partial derivative of H over T dt at constant P minus partial derivative of S over T at constant P. Now in here, we're using our calculus that the differential of the xy equals to x dy plus y dx. So this term, first term, becomes partial derivative of h over t at constant p times 1 to the t, and plus the h times the partial derivative of 1 over t over t. So this is actually a normal derivative, minus the partial derivative of s over t at constant p. Now this term, we know how to solve. This term, we solve it to be negative h over t squared. What about the rest? Now in here, we know that this equals to Cp. So the left term here becomes Cp over t. And the right term here, you'll have the partial derivative of s over t at constant p. So this also equals to Cp over t. And these two terms cancel out each other. So our final expression is proved to have the partial derivative of g over t over t at constant p equals to negative h over t squared. All right. Next up, using the appendix data to calculate the Gibbs free energy of formation. So let's write out that reaction first. So we start from our elemental form. We have 2 nitrogen gas and 2 oxygen gas forming your N2O4 gas. So that's a reaction of your formation. So your heat of formation of this reaction naturally equals to 9.16 kilojoule per mole. So these terms are all 0. So you get this number by checking the thermodynamic table. Your standard entropy of formation equals to the sum of your molar entropy of your different species. And you check the table. So for N2O4, we have 304.29 minus your reactant. So for nitrogen, it's 199.61 minus 2 times 205 plus 14. And keep in mind this is in joule per mole per Kelvin. So let's plug that in. 304.29 minus 191.61 minus 2 times 205 times 1.14. That's minus 297.6 joule per mole per Kelvin. And we're just using the delta F G naught equals to delta F H naught minus T delta F S naught. So we have, so this one is in kilojoule per mole. Let's make sure our unit is the same. 9160 joule per mole minus 298 Kelvin. 298 Kelvin times the negative 297.6 joule per mole per Kelvin. You plug in the number, you get, well, 9160 minus 298 times negative 297.6. That gives you about 97845 joule per mole. Or if we want to write it in kilojoule per mole, that's 97.8 kilojoule per mole. You can also check that number with the thermodynamic data to make sure you have it correct. All right, next up. It's a comprehensive problem, and let's read. For ammonia, the normal melting point and boiling point are known. The heat of fusion, vaporization are known. And you have the CP value for low temperature, and also the CP value for higher temperatures is given in the graph. Difference between ideal and real gives you 0.07 kel per mole per Kelvin. Okay, and let's see. In this question, what do we know? So when we're talking about CP that is low, you can just write out the things that we care about. So if we're looking at the molar entropy of 0 to 15 Kelvin, that's just equals to 0 to 15 Kelvin with like CPM low divided by T dt. That's just your CPM low over 3. And for the rest of it, for example, when we're looking at the entropy, we're effectively talking about the area below this triangle curve. All right. So let's get started with our question. First of all, calculate the SM 15 Kelvin. So we're looking at the equation here. What we have is your SM 10.0 Kelvin equals to your C naught PM T low divided by 3. Now this number is 0.176 divided by 3, and the unit is in kel per mole per Kelvin. And this effectively gives you about 0.059 kel per mole per Kelvin. So write that in, 0.059 kel per mole per Kelvin. Okay, next up. So this one we're talking about, next question, the difference between your entropy change between 195.36 to 15 Kelvin. So remember we did it in class, we're estimating the area below the curve of your Cp T dt. So in class we did that derivation to say this one equals to Cp d ln T. So what that means is if we want to find the integral of Cp over T dt, which gives you the change of your entropy, you can just use this area below the curve to estimate it. Now in this question, we're looking for the difference between 195 to 15. So 195 is the melting point to about 15 Kelvin. So you're estimating the area below the curve. So in this case, we're talking about this area here. Since this number is pretty small, you can estimate it as a triangle, or you can estimate it using the trapezoid equation. So if we're using the triangle, then we have 1/2 times 11.94 minus here. Over logarithm of 195 over 0.36 over 15. And you get about 15.10 calorie per mole per Kelvin. Or you can estimate it as a trapezoid. So the trapezoid equation is you have the 0.176 plus 11.94 times 1/2 times the logarithm of 195.36 over 15. And you plug in this number, you get about 15.5. So both of them should be correct. It's an estimate after all. The same applies to the next question. We're estimating this area here below between the boiling point and the melting point. So we're looking at the difference here. Right, so again, this one is estimated to be a trapezoid. So the area below the curve is 1/2. We're talking about the difference here and here. So that's 17.5 plus 18.12 times the height, the logarithm of 239.68 over 195.36 and times 1/2. And we plug in 195.36. This one is about 3.6. Okay, next up, delta S of the fusion. So this one is very straightforward. So delta S of fusion just equals to delta S of delta H of fusion over T fusion. And we read the question. The delta H of fusion is 1352. Divided by temperature of fusion is 195.36. 1352 divided by 195.36. That gives you 6.92 Kel per mole per Kelvin. Okay, next up, 4.5. By reading a thermodynamic table, one identified the standard entropy of NH3 equals to 50 kcal Kel per mole per Kelvin. And we know that the standard molar entropy at 236.68 is 48.43 Kel per mole per Kelvin. So calculate the heat capacity of your NH3 gas. Now the hint tells us our heat capacity is a constant. So that means if we're plotting or extend that plot of your heat capacity versus ln T, we're expected to get a straight line. Now the area below this straight line will be between your boiling point, which is 239.68, to your 298 Kelvin. Now logarithm of that temperature, of course. And we know the area here. So delta Sm equals to area. So this one is between your 239.68 to 298 Kelvin, equals to 50 minus 48.43. That gives me 1.57 Kel per mole per Kelvin. And this 1.57 equals to the area there. So that's a C naught PM times logarithm of 298 divided by 239.68. So solve for our PM, CPM. We plug in 1.57 equals to X times 298 divided by 239.68. We solve for CPM and we got that number to be, wait, did I do this correct? Oh, oh yeah, we're missing a logarithm, that's fine. All right, so this one is about 7.21 Kel per mole per Kelvin. And the reason I was pausing a little bit because we know the right answer of this value by checking the thermodynamic table. And if my number is too far away, you want to double check like if you set up your calculation correct. All right, and that's the end.